Thank you for watching Knowledge Academy. Okay, so what we're going to discuss today, we have two lecture topics. So we're going to split this topic into two lectures today and tomorrow. We're going to talk about use a double integral to representing the volume of a solid region and use properties of double integral okay. Okay, so what exactly they are saying is we're going to be using double integral to representing the volume of a solid. It means if I have a solid like a pretty much a trapezoidal shape kind of thing, it's like this shape. How can I find the volume by using double integral? Maybe the trapezoidal is a bit different. This kind of shape. So this one have like a both sides are tilt. You can see this side is tilt, this side is tilt. This one have pretty much this side is flat on the back, this side is flat on the back. The front side is have some incline. Okay. Another one you have like a you know uh, pretty much like a solid face for a cubical shape, right? You can do that one too. So that's the first thing we're going to talk about. The second one we're going to talk about evaluate double integral as an integrated. So it means we're gonna be also doing problems just like solving double integral without any application. Just if I gave you any function and I asking you solve the integral without any application like any shape or graphical representation, we can also solve it. The third one we're going to talk about is find the average value of function over a region. And what does that mean? Is like if you have a function like this, and this is a surface, and this is the area, right? This is all the area under the region. If I'm asking you, I need the average, like I want take this guy and then make an average. So what you can do, you can fill this one. You just basically taking this guy and then filling this area where it's going to be ended up. Maybe it's coming here, maybe it's coming here somewhere, maybe here. This is more appropriate. So what you're going to happen, you basically take this whole thing, just like that. You take this whole thing, put in a chopper, grind this shape into a little bit powder or pieces, and then fill the container, which is make sure how far it's going to go in the area. So this line is my average, right? So how can we do that? We apply the double integral if you have a function. And I want to know how you can find the volume. Definitely it could be a three-dimensional shape, right? And if I'm asking you make the average, you're going to be just do the same thing. You just take this one and then break into pieces and fill the container with them. And this is going to be like an average. So it's going to be somewhere here, maybe, right? This white color line. And this, the bottom part is the average. The average distribution of function. Really is average distribution of function over the entire region. Okay. So let's jumping into that. So what we learn about double integral, we learn double integral is writing like this, then dA. This is the area I'm talking about. That is my region. I can also write these double integral in the area domain, and I can split this dA in more like a parametric form, and I say r dx dy. Or I can also write this r is d by dx. Earlier we just did some function and some examples where we proved that either you do this and either you do that, both should give you the similar answer. Which one do you pick? Like dx or dy or dy or dx? It should be purely your choice. But the point is that if the function is giving, you have to wisely choose it. And the only thing is happen if you wisely choose it, it simplified your problem. Right? I mean, theoretically, both should give you same answer. The only hidden factor here is if your function is more in the y form, right? More have like a y form, and you choose the dx first. So what's happened? This function getting a little bit more complicated when you solve it. So you have to watch the function and think about it. Am I supposed to be doing dy first or dx first? Which way this function is easy to integrate initially? Okay. Another thing we notice that the function in each cases is actually 1. If I'm saying that, it does that mean is really there is a no function here but is 1. Maybe you don't have any function. So we also notice that these kind of double integral problems we solve through limits. For example, if I'm going to say that I have a function like this, that, and just says d, then it does not mention anything to you, dx, dy. So what you're going to do, you're going to take this function, like complicated function, something like this, you know, and then you're just trying to make a line like this, then make a line like this, then make a line like vertical line gonna go and then pass from the bottom. And then what you do, you're just taking this face, or this face, or the top face or the bottom face, and apply the limit here. So limit, then limit, right, then limit. Now these limits, what we're talking about here really is the walls or faces of the region you try to solve, or the solid you try to solve, right? Really, those limits are critical here. So you're not going to be writing like this. Most likely, you're going to be writing like, for example, we solved some problems where function is not even exist, right? We did some problem. We're going to be doing some problem more today, where function does not even exist. Nothing exists means what we have here. But you notice one thing. Usually, long time ago, when you do the double integral or integrals, you have a limit here, 5 to 0 or 0 to 2. But upcoming method in this topic, we don't use 0 and 5 or 5 and 0 all the time. Maybe we start using calling, let's go to x equals to 0, and here 2y plus 3. something like that. So really notice one thing, they no longer a just a numeric digit, right? Maybe they are, maybe they are not. So be ready for that. But pay attention on how this transformation is working. Right now I do not have any function, mostly. But if you have a function, I have to deal with this. But another important part is I do not have a simple limit. My limit's getting complicated. My limit's getting complicated, and right now limits are being changed to more of a equation. Okay. So let's take example as a sample how we can solve these kind of problems. Find the volume. Find the volume between xy plane and c, which is 6 minus 3x minus 2y above the unit square. I'm going to say unit square. Okay, and then unit square range is given x and y such that x go from here to here, y is going from here to here. Okay, function is not giving. Function is not giving. All we have to do, we have to solve ourselves and find out how we're going to solve this. I just told you a few minutes ago, this kind of function is not as you know used to be. A little bit difficult, a little bit different. So what you're going to do, not all, but not everything is simple. So I'm going to be trying to make this z 6 minus 3x minus 2y, and I'm going to take three-dimensional. Look like there is something, this is a z value. So if I put the z, let's put that this thing, if x and y equal to 0, both equals to 0, z equals to 6 minus 3, 0 minus 2, 0 equals to 6. So if both are 0, z equals to 6. So really, if both are 0, I'm going to go to somewhere here in 6 and then come out maybe, value of z somewhere here. And I can maybe put this guy here, z equals to 0, a little bit higher. That's my z-axis, this is my x-axis, this is my y-axis. So let's suppose z is maybe here 6. But if they're not 0, right? If they are not 0, maybe x equals to 0, right? If I say x equals to 0, y we getting some value, right? X equals to 0, z equals to 0, y we get some value. So this is my point where z equals to 6, and I'm going to come down this maybe this way, this way, this way. This kind of shape. It's hard to make these shapes because they are all over, but we get an idea like this is kind of a. So really this shape is look like we have a bottom, they have a square, then going up, up, this guy going really up. And so we connect these two, and then this. So really from this side, if you see, it's going to be look like this shape, like a taper. This taper face is the face we are seeing right here. Yep, this is a face. This is a face of taper face. Okay, I'm going to erase this thing. This is for understanding purpose. Now, what I'm going to do, I'm going to write my volume equation and tell you one important rule. In this problem, function is giving, look like yes, giving function z dy dx. I can also write, and I'm going to write r here, region, and I'm going to write here a function like this. And now I'm going to be replacing the z with the function which is giving 6 minus 3x minus 2y dy dx. Now in this equation, I'm saying dy dx. So really what I'm saying, I'm going to taking a piece like this piece, or maybe this piece from the bottom of this surface. And if I'm going to take that piece, it's going to be on the floor. Like this is the floor, xy is the floor. And I'm seeing from the top. My eyes is on the top. So if I see from the top, this whole area is going to be look like this. This is very important that how we see this projection or the direction of projection. So in this integral, we don't have a z involved. In this integral, we have no z involved. It means the thing which is not there, which is absent, that is the one I'm going to be using as a viewpoint. So z is my viewpoint. So if I'm going to see from the top, it's going to be look like this. This area, like this bottom portion. And you can see this little square here maybe, but this little square I draw is going to be here, but this square doesn't mean anything. This square means it's a dx dy patch, this one. And you see from the top, so this one is your x-axis and this one is your y-axis, because this is your x, this is your y. You take one or the other, but the value of x is given from 0 to 1 and 0 to 1. So this is 0 to 1 and this is 0 to 1. Okay, both are like this. And that is my r, right? This r we talk about. So what I'm going to do, I'm going to substitute here 0 to 1 for y and 0 to 1 for x. Okay, let's solve this. Now it's really straightforward. I also told you the rule, so make sure you understand and remember the rule. Whatever the operator is not there, that is the area you're going to be used. So if you're using dx, dz, what is not there? Y. So it means if you have any shape like this, whatever, you're going to be using y to see from this side. How this, if your eyes is here, how this look like from this side. So let's suppose it's a square or maybe it's a rectangle. From this side is going to be look like rectangle, and this is your r. And that is your x-axis and that is your z-axis. So you can take this limit and substitute for x, and you take this limit and substitute for z. So make sure we take a point how we can see these regions accordingly. Okay. I'm going to erase this. Just try to be putting this guy supposed to be 6, z equals to 6. We already talked about that. If you substitute x and y equals to 0, the answer of z come out to be 6. So what I'm going to do, I'm going to be solving this volume 0 to 1, putting a curly bracket here, and then 6y minus, I'm taking the derivative with respect to y, and then 3x derivative with respect to y is going to be 3xy minus y squared. 2 divided by 2 is going to cancelling out, or y squared is going to left over. And I'm going to close this parenthesis and apply the limit and then leave the dx outside. Before I do anything, I have to solve the limit or substitute the limit. So it's going to be 6, 1 minus 3 x 1 minus 1 square dx. So I'm going to say another step just for simplicity. I'm going to add minus. When you add y, everything becomes 0. The whole equation becomes 0. And then I'm going to close this parenthesis and says 1, dx. Okay. This guy. I think I'm going to simplify this one a little bit. So it's going to look like 0 to 1, then 6 minus 3x minus 1 dx. And if you solve further, it's going to be, maybe you can make it 5 is equals to 5 minus 3x dx. I'm going to solve this one. And this one is going to look like 5x minus 3 divided by 2 x squared, and the limit is 1, 0. If I substitute the values, it's going to be 5, 1 minus 3 by 2, 1 is squared minus 0. Okay, let's simplify it further. It's going to look like 5 minus 3 by 2, and this one is equal to, and minus 0 by the way, and this one is going to be equals to 10 minus 3 divided by 2, and this is going to be 7 over 2, and that is my volume of the region. Let's take other kind of example. Find the volume of a tetrahedron in the first quadrant. When you say quadrant is 2D, octant is 3D. I'm going to show you what is octant means. Octant bounded by, there's a function is giving 4x plus 2y plus 2, it's going to say z equals to a. That is my function is giving. This time function is giving, limit is not giving. See one thing, function is giving, limit is not giving. Sometimes limit is giving, function is not giving. This time function is giving, limit is not giving. What is by the way, we talk about this octant. Octant means, we used to learn about this octant in very first chapters of this course. But if you have a first quadrant, you call it quadrant, second, third, and fourth. This is a 2D. If you have a scenario like this, where you have these kind of quadrant, but you try to make it 3D, so you try to split into this further. So this is the first, second, third, fourth. The back one is fifth, and on the back side of this one is going to be another one. Make it 6th. Then back side is 7, and then it's this guy is 8, and this is called octant. So they are talking about to the first octant, it means they are talking about this one. So really this is a cube, or I can say it's a cubical domain. It's a cubical domain. So backside, if I'm going to draw this guy is z, we all know this is y, this is x. So inside this little rectangular cube, we have a tetrahedron. Inside the little cube, we have a tetrahedron look like, we have something look like this. So bottom line is that we have a shape which is look like probably. This is x, this is y. The equation of this function is giving z equals to, z equals to 8 minus 4x minus 2y. What I did, I just take the equation and then rearrange it. Okay, since we have a limited space, I'm going to erase this. And I'm going to go to my basic methodology. I'm going to say, yeah, I need to find volume. No problem. Volume equals to, I know this is a function, so I'm going to take two integral, and I know if I have a surface and I take two integral, I'm going to get the volume, right? This is my surface. Doesn't matter what surface I have. If I have this surface, I can make this guy and then find my volume. But in real life, double integral is not guaranteed you have a volume, because double integral, if you're taking this starting with the line, you may not end up the volume. So I'm going to do this one, and I don't know the function, so I'm going to say, yeah, I'm going to take z as a function, dx, dy, or dy, dx. Okay. This function pretty much same. I'm making a standard rule for myself. I usually do dy dx. Okay, you can do dx dy, it doesn't matter. It's pretty much same function. Now here I'm going to say is, well, I have the region where this is my x, this is my y. I'm going to see this function from the top. That's the rule. You're going to see from the top. If I see from the top, it's going to be look like this. That is my x, that is my y, that is my r. Okay. And I'm going to be talking about this definitely 0, 0, no problem about it. For this function, I'm going to put x equals to 0, and the other one I'm going to put x and z equals to 0 to find the y. Okay. So what I'm going to do, I'm going to write like this. Then I'm going to write two integrals, writing my function, which is a minus 4y, 4x minus 2y, sorry. Okay. And then dy dx. Here I'm going to substitute the value of y equals to 0, x equals to 0. That's the easy part. Other side, here, I'm going to take the y value. I need the y upper limit. So in order to find the y maximum limit, like go to y, because right now you see this region is this r. At this region, this point, z value is 0. At this point, z value is 0. Because if you are on the floor, you go all the way down to the floor of this cube, the value of z at the floor is 0. So what I'm going to do, I'm going to take my function z equals to 8 minus 4x minus 2y and substitute the z value equals to 0. So 8 minus 4x minus 2y. I need to find the value of y in the form of x. So I'm going to leave it here. So 8 minus 4x equals to 2y with minus sign. No, I think I'm going to take it on the other side. So it's plus 2y. Leave the y here. It's going to be 4 minus, I'm going to say 4 minus 2x equals to y. Okay. And from here, I'm going to substitute the value into my function. Y equals to minus 2x over 4. And I think yeah, I'm substituting 2x minus plus 4 minus sign. That is my y value. And I can say is y equals to this. I eliminate the z, I need the y value from there. And here, what I'm going to do, I'm going to need the x value, and I'm going to rid of everything. So if I'm going to rid of y here, I'm going to substitute further y equals to 0. I can find the value of x equals to 2. So I'm going to say, if y equals to 0, x equals to 2. 4 divided by 2 is 2. So that is my x limit, that is my y limit. I'm going to substitute these two values and good to go. I'm going to start taking my integral. So I'm ready to do that. And I'm going to take the outside integral, leave it here like this, and talk about the inner integral, which is with respect to y. Okay, and I'm going to write like this: 8 minus 4x minus 2y dy, and then apply this one: minus 2x 4 and 0, and then dx. Okay, if I take the integral, we just do it here maybe. Is going to be 8y minus 4xy, and then 2 divided by 2 is going to be 1y squared, so minus y squared. Close this, putting a big parenthesis: minus 2x plus 4, 0 dx. Okay, now I'm going to substitute the limit, the values into this. So volume equals to 8 minus 2x plus 4 minus 4x minus 2x plus 4 minus 2x plus 4 to the power square, and close this, then minus 0, then close this parenthesis. I think I should not close here, maybe this one. I can substitute another parenthesis here, and then call dx. Okay, it's going to be a little bit work to do to solve this one. So volume equals to, should be 2, is going to be 4, so minus 16y squared, 16x minus 16x plus 32 plus 8x squared minus 16x, right? And minus, now I'm going to be expand this 2x, or minus 2x plus 4 to the power square. I'm going to open this parenthesis by using the a plus b to the square identity, and it's going to be plus 4x squared minus 16x. 2 times 4 is 8, 8 times 2 is 16, 16x, and the square of the 4 is plus 16. Okay, let's try to simplify it if we can. So 16 here, 16 here, x minus, so I think we can canceling out this guy and this guy, plus and minus can canceling out. This 16x, and then this is there any x term? Yeah, these two x term can be added together probably, and this 8x squared and this 4x squared can be added together as well. So if I do this little math, my volume going to look like, I'm going to erase this guy. It's going to look like this: 4x squared minus 16x plus 16, and then dx. Okay, let's take a integral for this one. It's going to be look like 4 over 3 x cubed. I'm taking with respect to x minus 8 x squared plus 16x, and the limit is 2 and 0. Now I'm going to be substituting the value 4 over 3 dot this 2 times 2 times 2 is going to be a times a. X squared is going to be 2 times 2 is going to be 4 plus 16 2. Okay, and then minus, if you substitute the x equals to 0, everything becomes 0, so I'm going to say just like that. Let's simplify it further. I think we can do it. 4 times is going to be 32 divided by 3 minus 32 plus 32. This guy is cancelling out, so 32 over 3 is pretty much my answer, and that is my volume. This is the volume of the given region. Okay, to start this topic, we just talk about double integral, can be area, and it can be volume. Okay, and then we did a bunch of problems, look at all the theoretical aspect, and did a couple of 3-4 problems for practice. We continue that practice, and today we're going to be just wrap up this topic. So this problem, we have a different kind of applications are given. Find the volume under the graph of z equals to x squared above the triangular region with vertices okay. So in this problem we have a triangular region which is given to us, and the equation of triangular region is z equals to x squared. It means there is no y component involved, so probably it's going to be look like this, and then this is a y-axis, this is my x-axis, my z-axis, and there is a 3 vertices underneath. And maybe first I'm going to be drawing the region, right? There's going to be something like this, okay, and this is a region we are talking about. I'm going to fill with this with some color, right? This is the region we are talking about, but this region is basically lifted up, and we have 3 vertices underneath. Maybe one vertex is here, one vertex is on the back, right? Because this point is 0, -1, so it's maybe somewhere here, and another point is here. And whatever we need to fill between the two, between this is number 1, this is number 2, whatever we need to be filling in, it's very hard to draw, but this is a region. Yeah, this is a region we talk about. It's gonna look like this kind of region. You know, from the side, if you look, it looks like this kind of region, and the upper surface is 1, the bottom surface is 2. Okay. Now what I want to do, I want to be making a mathematical expression for this double integral, because it says volume and the curve is given or the surface is given. So what I want to do, I want to just writing z dy dx. Okay, dy is going from here to there and there to there, So from the first region, I'm going to be making from the top view. I'm going to start looking from the top. I told you the methodology. You start looking from the top, and from the top, when you look, that's your eye is going to be look like this region. That's your X. That's your Y, and it's going to be look like this. And the region is R. This is the region. This point is this point, right? And which could be Y is going to 1. This is 1, and this is minus 1. That is 1. And that is minus 1 underneath. So the coordinate of this, you can call it 0, 1, right? 0, 1. This coordinate you can call then 0, minus 1. Sorry, this one is going to be 1, 0. 1, 0. And this one is going to be 0, 1. This is going to be 1, 0. Let me just fix it. This is the region, and I'm going to be talking about this region. Now I told you we can make a vertical line law. So I'm going to make a vertical line like this line and move this line somewhere here. Okay, this line could be going from here this line could be going from this side to this side like this. Can be moved. So here it says extreme. Here it says minimum or lower limit. Okay, so I'm going to leave it here somewhere so we can talk about in general what's happening here. Now I want the equation of this side, and this side is equals to y equals to minus x plus 1. Right, this is pretty much the equation of a straight line if the two coordinates are given. This is I'm using a 2-point equation method, and here is y equals to x minus 1. Okay, so I need to do these 2 points. Those are my limit. So I'm going to apply here. I'm going to rewrite this expression. Right now I'm going to write the r. Now I'm going to substitute the value of z, which is x squared dy dx. And here I'm going to be saying my lower limit is y equals to x minus 1. Y equals to minus x plus 1. This is upper limit. And when you substitute the value of 0 and 0, both like y equals to 0 here, so x becomes minus 1. X becomes 1. So if you substitute y equals to 0, x becomes 1. Here we substitute y equals to 0, x minus 1, so x equals to 1. X equals to, now you have to substitute the value of 1 here, so x becomes 0. Okay, we're going to start doing this problem and substituting the value of 0, x equals to 1. And those are my limit if I don't want to be looking into that. If I want to be doing this way, I'm going to be making my line along this way. And if I move this line like this, these are my x limit, minimum, maximum. And if I go up, that is my other limit. So when I go there, this line is touching this x-axis, and this big x values become 0. When I go here and touch here, my x becomes max equals to 1. So I substitute these two values. Okay, let's start solving this one first and then the second one. So I'm going to solve this one and then do the second one. And I told you just writing like this will be a best way to avoid any kind of mistake. And here y equals to x minus 1, y equals to minus x plus 1. And this is my dx. Okay, let's do it. The first integral is going to be x squared y and x minus 1 x 1 minus x. Okay, and I'm going to be substitute the values, and this is a dx. Let's go further and substitute the limits. On the x squared parenthesis 1 minus x squared parenthesis x minus 1. Okay, if I do further simplification of this, is going to be x squared minus x cubed minus x squared plus x squared. Sorry, it's going to be cube x cubed, and then everything will be closed inside the parentheses and the dx. Let's see if we can substitute and clean some of the stuff. So minus 3 will be minus 2 cube x cubed, and then this one is going to be minus 2x squared. Okay. So 2x squared minus 2x cubed dx. Now it's further simple. I'm going to take maybe 2 common if I want to, or I can take simply integral. It's fairly simple integral to take it. So if I take the integral, it's going to be 2 over 3 x cubed minus 2 over 4, right? 2 over 4, but I can write 1 over 2 if I want to, and it's going to be x 4. Okay, that is my b, by the way. And here I have a 1, here I have a 0. Maybe I can say 1 over 2 just to make them very simple. And now I'm going to be substituting the value. Volume equals to 2 over 3, 1 minus 1 over 2, 1, and minus everything becomes 0 here. And I'm going to further simplify it. It's going to be 3 over 2 minus 1 over 2. If I take a least common multiplier, it's going to be 6. So 3, 6, and 2, 6, 6 minus. So it's going to be 6 minus 3. It's going to be 3 over 6. We can do half, and that is pretty much our answer. I'm going to go to another problem. Take a look into that one. This time we're going to be just solving this double integral without any wording. It's not a word problem. Okay, it's not a word problem. Remember I told you there is a 3 ways the problem being asked, double integral. The first one, they give you mathematical expression just like a double integral, simple, you need to solve it. The other one we have to give through words, but no mathematical expression. And the last one is you have to create your own expression by looking a image. The image is being provided and we have to look into the image to solve the integral. So let's do one another type where we have mathematical expression is given but nothing else. We're going to solve it and we're going to make a graph for that. Let's take a look at another problem. This problem, nothing is given as finding. And the integral is given like this. Limit is also given, so we don't have to worry about y divided by 2, and the upper one is 3, the lower one is 0, and the upper one is 6. Okay, that is a question, nothing else is given. We don't even have a choice this time, so we can say dy over dx or dx over dy. I mean, theoretically, you can write either, but problem is that in this problem is already given, so you don't have a choice to select what do you want. Okay, by looking this image, I know x plus y should be a straight line. This is a look like a equation of a line. This x plus y is the equation of a line. It cannot be a curve because there is no degrees involved. So if you substitute x equals to 0, y equals to 1, y equals to 0, x equals to something, right? So you can take, and if I both 0, you're going to start from here. If both are 1, you are here. Right? It could be, I'm just giving the one example. You could substitute any value and you're going to keep just growing this line. Maybe line is the line look like this, line look like this, is keep increasing as you increasing the coordinate. Okay, we are not interested much about in this line how this line angle. We suggest it's a generic shape. The one thing we know is the upper limit here is 3 because of that, which is x, and then y limit is 6, right? So this is x limit and the other one is y limit. Okay, and we just try to draw a line and say this is my region. And now let's start doing this problem and solving this. So I'm going to write the outer integral as is and try to solve the inner integral. And it's going to be half x squared plus xy. The limit is y by 2, 3, and then dy. If I substitute the limit, it's going to be look like 3, so it's going to be 3 squared to the 9 divided by 2, and 3 times just 3y minus, if I substitute half, sorry, y by 2. Let's say one more time, y divided by 2. And if I substitute the value, it's going to be y squared divided by 2 and then 4, so it's going to be 8. And 3, if I substitute here, so it's going to be 2 half 5. So if you add them together, it's going to be minus 5 over 8 y squared dy. We cannot simplify it much, but we can rearrange it if you want to. or we can just take the directly integral. It doesn't make much difference to us. So if I take the integral, it's going to be 9 over 2 y plus 3 over 2 y squared minus 5 over 2 3 is 8, so it's going to be 8 times 20, 8 times 3 is 24 y cubed. And the limit is 0 and 6. If I substitute the value, 9 divided by 2 times 6 plus 3 divided by 2 times 6, 36, and minus 5 over 24, and let me just see. Two 1 6. Okay, we solve this one, divided by 24, it's going to be 9. I'm going to write here. This one is going to be 3, 18 plus 18. So let me do this, and then this one is going to be 1 times 9. So 5 9 is 45, and 18 times 3, 54. Right, and this one, sorry, is going to become with minus sign. Okay. 54 plus 18 minus 45, going to be 27. It's going to be 27, my bad. This guy should be 27. 9th is 27. Let's do one more time. Okay. Going to be 36. Okay. And the reason we just did that is going to be this one. Maybe I can substitute the value of 3, y 6. If I substitute 3, that is my region, basically. Okay. Usually we don't write the formulas with units. When we're writing those numbers, we don't write with units, we just write them. But technically, you should have any quantity. So this problem, the only yellow text is given, and the rest of us we have to create. Okay. Really, you don't have to. Do we really need to create this graphical image? Not really. If you need to solve this, you just need to solve just like you're solving any integral. Okay, now we're gonna be doing another problem, and that problem is kind of wordy plus the bound. Like the expression is given and also the words are given. Like an expression is given. How you're going to create the limit. So that's a tricky problem. When I say tricky, it's not mathematical challenge. It's basically a understanding challenge. How you can understand the problem. So problem is this: evaluate the double integral the problem is giving something look like this: x, y, t, a, r. In R, the extension is given rectangle with vertices, 0 0 0 5 3 5 3 0. Okay, I'm going to say solution and take a look on this given information. XY looks like XY is simple area equation. You know, when we writing what is the area of a rectangle? Length times width, or length times height. Sometimes people say length times breadth. I'm going to make this, and I'm going to say is, you know, making some rectangle. Maybe it's rectangle, maybe it's square. I'm not 100% sure. I'm not really 100% sure this look like a shape. It's a rectangle and a square. I make a rectangle. Okay, this look like a little bit taller, but not too much wide. But I'm gonna looking here. 0 0 is my 0 0 this point. The other coordinate is my 0 5, right? So maybe I'm gonna say 0 5 should be this point. Look like to me. The other one is 3 5. So 3 5 is this, and then 3 0 is this. And that is my R. Okay. Now I'm gonna be start doing this problem. But when I did this problem, I want to apply my rule for vertical and horizontal. Okay, vertical and horizontal lines. So I'm going to make this line. Maybe I can make a line like this, and I'm going to make another green colored line maybe somewhere here. You can move these lines like, you know, you can move these lines back and forth if you want to, right? But does not going to make any difference because the shape is pretty uniform. Same thing if I move this line, it's not going to make any difference because the shape is pretty much constant. So what I'm saying in these other words, if I have a shape like this and you're making a line, then this line, if you move this line up, is going to be touching here and touching different location. You know, keep changing. But in this case, since we have both sides, if I move it up and down, these 2 points is going to be again same points, cutting. Okay. So what I'm going to be just writing this expression a little bit again, and then says dy, dx or dx, dy. It's really up to us. How do we pick those? So I'm going to pick dx. Dx means y is constant. Here I'm going to say y constant. And for this, x is constant. Right. So what I'm going to do, I'm going to be just substituting the limit and limit for dx. Dx going from 0, and here is 3. So maybe I can write 3, 0 to 3. For dy is starting with 0 and then hitting maybe 5 here. Right? These are the 2 points I'm interested, and these are the 2 points I was interested for x. This is my dy constant where x is, you know, the green line x is constant, and that is my y limit. So 0 to 5. Okay, let's solve this one. 0 to 5. Then I'm going to be writing half x in x y squared x squared y plus, that's pretty much it. It's done. And then dy. And I'm going to apply the limit, which is 3, 0. So let's apply. And 3 to the power 9 y and minus 0. Everything becomes 0. And then dy. Okay. Can we simplify this? Probably a little bit, not much. So 9 over 2y 50 dy. If I solve this one, it's gonna be 9 over 2 times 1 over 2y squared and then 5 0. Okay, so it's going to be 9 over 4, 9 over 4 dot, and then y squared. I'm going to substitute the value for y squared directly, so it's going to be 5 squared minus 0. If I solve this one, it's going to be 9 over 4 times 25, and let's see what we got. Yeah, it's going to be 225. That is my answer. I'm going to start one quick problem for a different topic, the one we just talked about in the beginning. We're going to talk about average value of function over the region. Okay, let me just go to the next slide. Talk about average of a function over a region. You know, and this topic is fairly, it's just like a rewriting double integral in a little bit different way. And then how does it work is that, let's suppose if I have a random shape and I ask you calculate the area under the volume, and you basically calculating this R, and you're calculating the volume of this solid. So you calculate the volume of this solid. Now it goes up to high. Let me just make up some numbers. So it's pretty high. Like suppose this guy to this guy is maybe 25 feet, like 25 feet. I don't care about the width, maybe width, whatever is there, right? This is 35 feet. What we want to know, this is a function, right? This is my function curve. This is my function. What I want to get the average mean. I want to chop this area and then fill, making an arbitrary domain. Like I'm going to fill this guy up, I fill this guy up, and I'm going to fill. So what I'm going to do, I'm going to make like a container, right? And I'm going to just crush this whole region, this white, this yellow color solid, and crush them and then fill it out. So this is going to be filled out, the white color one. And this line, this green line, we can say that this green line area is my average of the function. And how can we write this thing in a mathematical form? If f is integrable over the plane of region R, then the average value of f then the over R is written by like this. You're going to take the actual area. Which area? The bottom area. This container area. I'm talking about the bottom. So it's going to be look like from the bottom is going to look like this. That is my area. And if I'm not writing simple double integral, all I can do is just write in double integral the way we used to write. Okay. Where A is the area of R. Right. Just A is the area of R. There's nothing new topic, it's just a application of the thing we just discussed. So let's just do one problem. Let's take a look at another problem. Find the average value of f x y. This my function is given half x y. That is my function over the plane region R. Where R is rectangle with vertices of 0 0 4 0 4 3 and 0 3. Okay. So what I want to do, I want to make a arbitrary image. It's what is given. You don't have to create it, but if you create it, it's definitely going to help you. And this is my region, guys. This is 4 0. This is 4 3. This is 0 3. And this is 0 0. Okay, that is my area. And that is my area, and then basically, but this is my region, R. Right? And the function is giving like something, a yellow color one, maybe. This function is going up, really spiky because of half xy. And it's pretty much a straight line, but look at the curve, but this curve is going to be touching here, and it's going to touching here. And that is the surface you have. This is the surface. It's basically like a wrap going on the other side too, right? Okay, I simply just multiply them 4 times 3 because this side is 4 and this side is 3. Other than that, I'm going to be just doing the values just like I used to do it, nothing new. I'm going to be just writing average value equals to 1 over a r function f x y and then d. I can also write this one like this. half x y dy dx. Dy is going from 0 to 3 and dx is going from 0 to 4, right? So let's solve it. 1 over 4 and xy squared. Apply the limit 3 0 dx and solve further. It's gonna be 3 times 3 is gonna be 9 over 4. I'm gonna take it out and then leave it inside 4 0 x dx. Okay, let's solve this one as well. Maybe we can simplify. This one is 3 minus 4, so it's gonna be 3 over 4 times 4 is 16, so 3 over 16. Inside the integral, I'm going to be just doing it direct. Integral 1 over 2 x squared 4 0, so 3 over 16, and then 4 times 4 is 16 over 2 minus 0. Okay. Maybe we can multiply the 2, so it's going to be 3 over 16 times 16 over 2. These are cancelling out, so 3 over 2 is my which function? This function. Okay. All right, this is pretty much we have the content for this. We did a lot of practice and different problems, different categories and different types of problems. And I told you mainly 3 problems we have. One, double integral can be a little bit challenging if you does not use these parentheses and making mistakes. Also, sometime I wrote like this. Make sure you guys getting those. Do not take it light. Sometime I write like those. You see, x equals to 2 and x equals to 5. And the reason I'm just writing like this because when you take the integral, you have this kind of stuff, right? Like just exactly this way my cursor is like this one. How do you know this 3 is basically is a limit for x or 3 is a limit for y? So if you put the limit, you're making a mistake because if you're putting this limit on x, the next integral you do it, that will be basically wrong, but you don't even realize because it looks pretty much normal. Because y squared dx, you're going to say, well, y squared is constant, so just including one x here and good to go. So make sure that when you want to be writing like this sometime to make sure you catch up the difference between 2 variables. Other than that, we have 3 kind of problems are given. Number 1 problem, just integral is given. If you don't have anything else, it's given. Number 2nd problem is that you have a function is given, right? And you have like some through words that explain to you the limit. You have to create the limits, like what we did in this problem. The 3rd kind of problem, nothing is given, but just a picture graph, and you have to create in, and maybe they can put here and say this is half x y squared, right? And by looking this, you have to create the double integral by your own. Writing like this says, oh, this is my function, something like that. So we did all 3 kind of problem and multiple problem for all of them. Thank you for watching Knowledge Academy. Please subscribe my channel.